Okay. Oh, you know what? That's why. You know why I can hear an echo? It's because it's coming through my phone, so I can hear it on my phone as well. Okay. So let's see. So last time I think I left us with the following exercise. So I was talking about Heine-Borel, and it's this fact that in Rn, maybe we can just repeat it. So theorem. And yeah, I didn't get an opportunity to see if I could think of a way of proving the opposite direction without sequences. Maybe it exists, maybe it doesn't. I'm not 100% certain. But Heine-Borel states that a set in R, really in Rn, but a set in R is compact if and only if it's closed and bounded. So a set S in R is compact if and only if S is closed and bounded. And I was chatting with the TAs, and apparently Spivak, if you check Spivak, Spivak states Heine-Borel as, you know, a set is compact if and only if it's, what is it? Heine-Borel in Spivak is that the closed interval AB is compact. And I'm like, no way, that's not Heine-Borel. It's close, it's related, but it's not Heine-Borel. So we're going to ignore Spivak's, what Spivak thinks is Heine-Borel. We're going to use this, which is what the rest of the civilized world thinks is Heine-Borel. And so basically, what does it say? It says this weird condition of every open cover having a finite subcover is equivalent to your set being closed and bounded. And so again, you might say, well, then why do we even talk about it that way? Well, it turns out there are lots of cases where it is much easier to talk about open covers and finite subcovers than it is to talk about closed and boundedness. And when you generalize into more general topology or into different metric spaces, these sorts of things, basically, once you leave Euclidean R, this definition of being closed and bounded doesn't give you any of the things that you want, right? So you really have to use the open cover definition there. So one of the things that I think we should do is prove the following theorem, which I think is very nice, right? So on Tuesday, I proved one direction of Heine-Borel, but I said I couldn't prove the other one because we didn't quite have the tools yet. But in February, if you remind me, I'll go back and I'll do it again and show you the opposite direction. But here's a theorem. And I think I left you with this and said to try it. Whether or not you tried it is, of course, a different story. So suppose, or if F mapping R to R is continuous, and K is compact, then F of K is compact. Right? So did anyone try this? Did anyone manage to get anywhere on it? There's a sense in which, you know, if you just set up the question correctly, there's really only one thing you could do, right? No one tried it? Okay, that's all right. So what I want you to do right now, spend a second and try and think about what you would do in this case, right? Like, how would you actually try and prove this? So what are you trying to show? You're trying to show F of K is compact. Okay, you could try and show that its image is closed and bounded. That's a little bit rough. But even more importantly, if we prove this using the open cover definition, like I said, that proof will actually work always, even when we leave Rn. So maybe we should try and take that approach. But if you want to try and prove that the image of a closed and bounded set is closed and bounded, you could try that. That would be fun. Okay. In fact, it's probably not, let me think about this. It's probably not too hard to show that the image of a bounded set under a continuous function, of course, should be bounded. And in fact, if you use the extreme value theorem, you get that for free. But no, that's not necessarily true. I would be hesitant to say that, but that one's not too bad. I think the hard part of this is going to be proving that the image is closed. That generally is not going to be true. So yeah, that one's I think going to be the tougher one. But this proof ends up being pretty easy from the open cover definition. So what do we want to do? We want to show that every open cover of f of k has a finite subcover, right? Every open cover of f of k has a finite subcover. All right, so what are we going to do? Let's choose an open cover. Be an open cover of f of k. Okay, right, still haven't done anything. All I've done is kind of set up the problem. What is it that we're trying to show? Yada, yada, yada. And at this point, again, you kind of get stuck and you look at your assumptions and you say, well, what do I know? Well, I know f is continuous and I know that k is compact. Okay, so maybe I can use that somehow. And in particular, what I might want to do is say, well, I know that every set in O is open. So their preimages are all open, right? That's just how it works for continuous functions, right? Preimage of an open set, continuous preimage of an open set is open. So I should be able to take this open cover, and if I take all of the preimages of those things, they stay open. So that's good. And then I know that K is compact. So if I take the preimages of those things, hopefully they cover K. And if they cover K, then I can just reduce them to a finite subcover of K. And then if I push them back onto f of K, hopefully that'll be a finite subcover of f of K, right? So that's the idea. Let's take the preimage of our cover, hope it's a cover for K, reduce to a finite subcover, and push it back, right? So we're really using compactness and continuity there in order to do that. Right, so what we're going to do, so let O be an open cover of K. So for each U in O, right? So this is an open set. Consider F inverse of U, which we know is open. Since F is continuous. Okay, and what we're going to do is we're going to find a new cover. Let's maybe call it like O hat. So let's define O hat to be the preimage of the other cover, right? Which we claim is an open cover for K. Okay, so certainly all of the elements are open. We don't need to check that. What we do need to check is that it is actually a cover, right? We actually need to check that if I take the union of all of these things, it completely envelops K. And to prove that, all I need to do is prove that every element of K is in one of the covering sets, right? So let's fix some X in K so that f of X is in f of K and hence in some U. For some U in O, like that, right? Therefore, X is in that preimage, right? So thus, X is in the preimage of that set, right? Because that's what it means, right? X is in the preimage if f of X is in U. So thus, X is in the preimage, which is an element of our O hat. And so K is contained within the union over O hat. Well, I guess how have I been writing this? I think I've been writing it like this. I don't remember what I did last time, but I think I've been writing it like that. Okay, so yeah, this is a cover. All right, so now it's a cover for K. We know K is compact, so we can reduce to a finite subcover. So since K is compact, there is a finite subcover. And let's give it a name. U1 ... UN. I guess I should write it as F inverse because that's what all the elements in O hat look like. So let's say F inverse U1 ... F inverse of UN. in O hat. And now we claim that U1 through On is actually a finite subcover of f of k. Now we claim that U1 dot 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 UN covers K, right? And therefore would be a finite subcover, or sorry, f of K. And so now we need to check that. So again, we're going to do the same sort of thing. So let Y be an f of K. And choose some X in its preimage. Such that Y is equal to f of X. So that means that, right, like we said, X is in K. So X is in one of the preimages of UI. Thus, X is in F inverse UI for some I, which implies that, okay, so what does this say? So this implies that f of X, well, that's equal to Y, is in UI, right? So yeah, that's what we wanted to show, right? We wanted to show that no matter what element I chose of f of K, it's in one of the U's in order to show that the U's actually cover it, right? So hence f of K is contained in the union. Oh, that's just a U, not a union. Union from I equal 1 to N of U sub I and U sub 1 dot 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 UN is thus the finite subcover. Right, and there we go. So that's pretty cool. This, like, I think this proof looks long, but it's long just because there's a lot of writing, not because the concepts are terribly difficult, right? Again, there's a sense in which I claim that this is the only thing you could have done, right? Start with an open cover for f of K. What are you going to do to it? Now you're going to bring it back to an open cover of K, use the compactness, and then, once you've gotten a finite subset for K, push it back to f of K. And yeah, like I said, this is the only thing you could have done with the tools that you were given. So even though this proof probably on first glance looks a little bit extreme, it's really not, right? Like it's not too bad. So for example, I like this proof. Here, let me state an immediate corollary of this. And of course, we've already proven this theorem, but this is how I prefer to do this. So you remember our proof of the extreme value theorem where you have to do this like weird forcing argument? You say, let, take the set of all B where F achieves its, what is it? Like, oh man, what did we actually take that set to be again? So with the intermediate value theorem, we took it to be the collection of all points where F stayed beneath 0. And then we took the supremum of that. Oh, it's bounded. Yeah, right. We needed to prove this boundedness result. So we said, take the collection of all the points B where F is bounded on the interval, X. Take the set of all points X where F is bounded on the interval AX. And then we took the supremum of that set and showed that it was the whole interval and then used that to prove the extreme value theorem, yada, 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 blah, blah, blah. I hate that proof. I really don't like it. So I think that this proof, even though it maybe looks intimidating, is actually much nicer. And from it, the extreme value theorem is now immediate, right? So if F maps K to R, where K is compact, then F achieves its max and min on K. Okay, and what's the proof of this? Well, the proof is we just showed the image of a compact set is compact. So its range, f of K, is also compact. Oh, I guess I should say if this function is continuous, right? Obviously, we need continuity. So we know that f of K is compact. And by Heine-Borel, it's therefore closed and bounded. Okay, bounded implies that sup and inf both exist. Right, so the sup and inf exist. And while we haven't formally proven this one, I'm going to give you, this is something you can check for yourself, and you can probably convince yourself as well. Closedness implies that the sup and inf are actually in the set. Implies the sup and the inf are actually in f of k. Okay, and we're done. So therefore, they're actually maxes and mins, right? They're not just the sup and the infimum, they're actually the maximum and the minimum. So you can check that one for yourself. This proof is not crazy. Basically, you just want to convince yourself that the sup and the inf are boundary points. And we were talking about that, I think on Tuesday. If not Tuesday, then certainly the previous Thursday. But yeah, remember we were talking about how the sup and inf were boundary points. And that's, if you really want to prove that they're boundary points, use the definition of sup and inf, right? So maybe as a little aside, let me just remind you what that means. So M is the supremum of the set S if for every epsilon greater than 0, there exists some S in S such that M minus epsilon is less than S is less than or equal to M, right? But what you'll notice, this is precisely the left half of the ball centered at S, right? This is part of, so normally, what do I want to say here? i.e., maybe let's kind of rewrite this, i.e. S is in M minus epsilon to M like that, right? Exactly, it's the left half ball. So what you get is you're guaranteed that that epsilon ball must intersect the set S, right? But because M is also an upper bound, the right half of the ball must intersect its complement. Does everyone agree? Right? Like the right half of the ball, M to M plus epsilon, can't intersect S. Why? Because M is the least of the upper bounds, right? There certainly can't be any element in the set S, which is bigger than M, right? So the left half ball intersects S. The right half ball must intersect the complement, right? And if you really want to formally write that out, you can be like, for the sake of contradiction, suppose the right hand ball doesn't intersect the complement. That means that everything on the right half, M to M plus epsilon, is in S, but that contradicts the fact that M is an upper bound, right? So the right half ball intersects the complement. And so this is a boundary point, right? We've shown that no matter what epsilon you choose, you intersect both S and its complement. So the supremum is a boundary point, right? And you can imagine the exact argument works for the infimum. Right? And so if you're closed, like we said before, if you're closed, you know that you contain all of your boundary points, namely that your sup and inf, now there could be other boundary points, but in particular, your sup and inf are actually part of your set, right? And so that's what I'm saying above there. When we say closedness implies that the supremum and the infimum are in f of k, yeah, we get that for free. So now you can see the extreme value theorem is actually relatively easy to prove. Like I think, for me, even though there's a fair amount of writing here, the ideas are relatively simple and much simpler in my mind than the ideas that we used in order to prove the extreme value theorem the first time that we did it, right? Like that argument is kind of, like, why would you define that set to be that way? Okay, like, I guess it works, right? Like, maybe. But yeah, this proof is, to me, very intuitive, very natural. And yeah, I mean, this is definitely my preferred extreme value theorem. Okay. And remember so there were 3 theorems that we did that were like this, right? So one was the extreme value theorem that had this kind of weird forcing argument proof. One was the intermediate value theorem, right? And then the other one was the fact that if you're continuous on the set AB, then you're actually uniformly continuous, okay? So the intermediate value theorem does have a proof like this as well. It requires that we introduce the notion of connectedness, and I don't think we're going to get there, even though it's kind of the next natural thing that we would talk about. But what I can state, and maybe I won't prove it though, but what I can state is the theorem. And this is very nice. And again, if you prove it using the open cover definition, it immediately generalizes to, other spaces, other topologies, other metric spaces, that sort of thing. So if F mapping K to R is continuous and K is compact, then F is uniformly continuous. Now, uniformly continuous, there isn't a great topological definition of uniformly continuous. Like we said, the topological definition of continuity that we want to use is precisely this idea that the preimage of open sets is open, right? That is the correct way of topologically dealing with continuity. Uniform continuity, there is kind of a topological notion. Again, it requires sequences, but there isn't one that really involves open and closed sets. So for this one, we would want to use the epsilon delta definition. But again, this proof ends up being like incredibly intuitive. There's a little place where you have to be a little bit careful, but the intuition is clear. So let's think about what it is that we want to show. So we want to show that for a fixed epsilon, there's one delta that works everywhere, right? So let me give you the idea, because this is a really easy one to do. And for example, it's much easier than the proof we gave. So I really do want to leave this one as an example, but let's talk about what the idea is. Okay, and let's see if you can mathematize that idea. So we want to show that for a fixed epsilon, there's one delta that works everywhere in your domain, right? That it doesn't matter where you are in your domain, that one delta will always work. It doesn't depend on the point that you're looking at in terms of continuity, right? So we want to show that for a fixed epsilon, there's one delta that works everywhere. There is a single delta. And of course, when I say single, I don't mean there's a unique delta that works everywhere, but I mean that there's one delta which works everywhere and it doesn't depend on X. There's a single delta greater than 0, which works, which let's say shows continuity. For every point X in K, right? And again, we can always take a smaller delta. That's not what I'm saying. I'm saying there's only one. It doesn't depend on X, okay? So the natural thing to do here is to say, well, I know that for every point in K, right, my function is continuous on K. So for every point, there is a delta which works, right? So, so here's the idea. 1, for every point, X and K, there is a delta. And I'm going to call it delta sub X, just so that, we're reminded that it does depend on X right now. We eventually want to remove the X dependency, but we're just going to say for now, we know it depends on X, right? There exists a delta X, which works. So what we're going to define, so let's define similar to what I did before. So let's define B sub x to be the delta x ball centered at x, right? And so this is certainly open, right? And again, this delta x ball is the delta x ball that works for continuity, right? Every point in this delta x ball is going to be within epsilon when you take f of it, right? Maybe let me kind of put that in. So we're going to have that f of b delta x is contained within the epsilon ball of f of x, right? This is the definition of continuity, that this is going to be true. So now what we're going to do is we would take an open cover, right? We're going to define an open cover just to be like all of these balls, right? So let's say define O to be the collection of all of these balls. And that's certainly an open cover. Right? It's an open cover because, well, every single one of these things is an open ball, so they're certainly open. And we've done this, like every x is certainly in the delta ball, right? And we've done this for every single element x and k. So yeah, there's a lot of balls in here, right? Potentially there's uncountably many balls that we put into this open cover, but we've definitely hit every single point. We overlapped, like we've definitely have a lot of redundancy, but we definitely hit everything. Okay, and now 3, take a finite subcover, because K is compact, right? So take a finite subcover. Okay, let's call it BX1, BXN. And remember, each of these balls has a delta X. So what you probably want to do is take the minimum of those balls. Take the minimum, like let's say take delta to be the minimum, delta to be the min of delta x1, delta xn, and show that this delta works, right? Basically what we're saying is you've got all these delta balls. You know that every single point in K lives in either bx1, bx2, or ... in bxn. And therefore, there are these finite delta x1, ... delta xn, which give you, your definition of continuity. And so you're trying to show that there's one delta that works. So if you take the smallest of all of these deltas, that should work, right? And you're basically done, okay? And so that's it. So there's the idea. I've kind of created this program of like what you would want to do in order to be able to prove this. You just now need to go and verify each step. Now I am sweeping a little thing under the rug here, right? Just a little thing that you do have to be careful about. And I don't put this in the program because it's a little bit annoying, but the only thing you have to worry about when you do this proof is the following. So let's say here's x1. Let's say here's x2. Again, we know that they have delta balls which cover the entire set. Maybe let me just draw this a little bit bigger. Okay, so we've got here this is b delta x, or bx1. Right, so this length here is delta x1. And then I've got something like, bx2. And so this length here is delta x2, okay? And again, we're going to take the minimum of all the deltas to make sure that they work. The only thing that we kind of have to be careful about is, well, if you take the minimum of the deltas, the distance between, I need to use a different point. The distance between this point, let's call this y, and the distance between this point, z. Actually, I guess I could have done this within a single ball, but whatever. This distance could be bigger than delta. Right? And that's an issue because I need the distances are, I need the result to be true as long as the distances are always less than delta. So that's fine, right? The reason why this works at a fixed point x1 is because you're always looking at the distance from x1. And so everything, yeah, let's just ignore this ball. I don't think this ball actually matters. So we're always looking at the distance from x1. And because x1 is in the middle of the ball, there's no point in this ball is further than delta away from x1. But now if I choose 2 points in this ball, they could be further than delta x1 apart from each other, right? And that's a problem because they need to be less than delta x1. So the way that you fix this in this proof is that instead of, where did I do it? Here, instead of taking the delta x ball, you actually take the delta x divided by 2 ball, right? Because if this distance down here in the blue, if this distance is now delta x divided by 2, then the furthest away that 2 points could be in this ball is delta x1, right? And so now that will work. So you might have to think about this and convince yourself of this. Like, hopefully this program isn't too intimidating, but that is kind of the only thing that you have to be careful about, is that there is a delta x divided by 2 right here. And you have to say, oh, well, why did I need that? Precisely for the reason I just said, that if I give you any 2 points in the delta x ball, they could actually be more than delta x apart. Okay. Does everyone understand like the outline here of what you're supposed to do? Is there any questions about it? Yeah, good. Okay, that I'm happy that the delta over 2 makes sense, right? Because this is one of those things that when you write up the proof, the students are just like, wait, hold on, why are you putting delta x over 2 there, right? And in fact, the first time almost anyone proves this, they don't think about the delta x over 2, right? They just use delta x. And then they get to the end and they're like, damn. Yeah, this isn't going to work. But can I fix it? Oh, yeah, I can fix it by using delta over 2, right? So that's just kind of caveat to be aware of. But yeah, if you put that delta x over 2 there, or over 4, right? Like, just make it as small as you want it to be. Then everything magically works out, right? And it becomes very, very nice. So yeah, that's it. Yeah, unfortunately, I don't think I want to talk about connected. Maybe I'll just define it just so you have it in front of you, and then you can try to do all the things that you want to do. So let me just define connectedness for you. Okay, so definition. So a set S in R. What can we do with it? So what I mean by this is, well, here, I'll give you a bunch of exercises you can do as well, okay? So set S in R is connected or is disconnected. So this is kind of the weird thing that we do with connectedness, is that we don't actually define what it means for a set to be connected. We define what it means for it to be disconnected. So the set S in R is disconnected if S, or let's say if there exists non-empty sets A and B such that, what do I want here? S is A union B and A bar. So remember, this is the closure. The pair, in this case, the pair AB is a disconnection of S. If S is not disconnected, it's connected. Okay. So again, hopefully this definition is somewhat intuitive. I'm willing to bet that if there's anything giving you trouble, it's probably this thing right here. But let me give you a couple examples. Okay. So for example, right? If I take S to be 0, 1, union the set 3, this is disconnected. Right? So we'll take A to be 0, 1, and B to be 3. Right? So A is, or S is certainly the union of these two sets. Yeah, exactly. They don't have the same boundary points. That's exactly what that condition there guarantees. The thing that's underlined in yellow, it guarantees that they don't have the same boundary points. Yeah, so that ends up being important. Exactly. Right? Okay, so this is like an obvious set that's disconnected, right? Like there's a big gap between 0, 1, and 3. And so we're going to take A to be 0, 1 and B to be 3. S is certainly their union, and then their closures, both A and B are actually closed. So they are their own closures, and their closures don't intersect. Okay. And now you might say, okay, well, so that's the easy example. Why do we require this closure condition? So basically what I want to be able to say is this set is connected. Right? I can't write it as two parts. If I don't require this closedness condition, this weird closure condition in the top right-hand corner of the screen, if I don't require this, I run into the following issue. Right? Yeah, exactly. If Divyansh, if it were like, yeah, if the interval was a little bit bigger, exactly. So I did 0, 1 here, but you're right. If I did, actually, you know what? Let's do yours. Let's do like 0, 2. I guess, yeah, and then let me use something similar to yours. Let's maybe do 0, 1 like this, and then 1 to 2. So that's kind of in line with your example, right? I think your example was a little bit different, but it was basically the same. And yeah, exactly. You run into this issue where S is the union of these two sets. These two sets do not intersect each other, right? But we run into this issue that no, this should not be a disconnection. 0, 2 should be connected, right? So we require the closure condition to guarantee that this can't happen, right? That there actually, basically the closure condition guarantees that there actually has to be space between A and B, right? Like there has to be a little gap there. And then the reason why, so you might say, well, then why don't we just do the closure of A intersect the closure of B, right? Like why do we take one side, close one side and not close the other side? And the reason for that is because we want this set to be disconnected. Yeah, exactly. Right? So I want that if I take something like 0, 1 union 1, 2, this set is actually not connected, right? There's a point missing, right? There's a gap between 0, 1 and 1, 2. But in my condition that I underline in yellow at the top right-hand corner of the screen, if I use the closure of A intersect the closure of B, these two things, right? This is evidently A here, and this is evidently B. If I use the closure of both, they would actually intersect, right? Because these two things do actually have a common boundary point, right? So I only want to use the closure of one set and then intersect it with the other, not the closure of both sets, because it is possible that the sets become arbitrarily close. What I'm trying to guarantee is that there's actually a missed point, right? And the closure could capture that missed point. So I don't want to use the closure of both sets. Otherwise, they could actually intersect. So does that make sense? And like when we do this in 257, this is actually a fun little exercise that we usually do as a class, which is how would we define what it means for two sets to be disconnected? And then they usually come up with the condition in the top right-hand corner, but without any of the closures. And then I say, okay, but what about this set, right? Should this set be connected? And then they modify it a bit. They usually put the closure over both sets. And then I give them this example. And then they're like, oh, let's only take the closure over one. And so it's a really fun exercise when we do it, in that usually in 10 minutes, we can figure out what the right definition is by me saying, propose to me a definition, and then I'll give them a set and say, does this do what we want it to do? And that sort of thing, right? So it's very nice like that. Nice little exercise. Okay. Explain the 0, 2 example. Okay, so what I'm saying is, so this should be connected, right? I think we agree that 0, 2 should be connected. It doesn't have any gaps in it or anything like that. If what I'm saying here is the reason that this is not a good condition okay, we don't just want to say A intersect B is empty, because here I can write, S in terms of A and B, right? S is their union, and A intersect B is empty. So if this is the condition that we had put up here, then this set would actually be disconnected. And we don't want this set to be disconnected, right? We want this set to be connected. So that says that we can't use this condition. This condition is bad because it would lead to pretty much every set being disconnected, right? And so that's a bad condition. So we need the closure in order to account for this sort of case. Does that make sense? Hopefully. Okay, so exercises. Number 1. The closure of A is the union of A and its boundary points. Right? We talked about that one on Tuesday. So you might need to go back and just look at the Tuesday stuff. Right? It was the smallest closed set containing A, for example. That's one of the things we proved. Okay, so exercise number 1, a set S in R is connected if and only if S is an interval. Okay, so the only connected sets are precisely the intervals. That's it. That's not going to be true outside of R. Okay, in R2, R3, it's certainly other things. They're not just like balls. There are definitely different kinds of connected sets. What else do we want to prove? So if F mapping R to R is continuous, and I in R is connected, then F of I is connected. Okay, so you'll notice exercise number 2 here is the exact same as the compactness, just we switch compactness with connectedness, right? So with compactness, we said the continuous image of a compact set is compact. With connectedness, the continuous image of a connected set is connected, okay? 1 is hard. 2 is easy. Which I think is a little bit surprising, right? Because I think 2 looks like the scarier statement. But no, it actually turns out 1 is quite difficult. 2 is fairly simple. Okay. 3, the intermediate value theorem is immediate corollary. If F maps I to R is continuous and I is connected, then for every, what do I want to say? For every C and D in F of I, there exists a theta in I. Or yeah, here, let me say this. So for every C, so for every F of X and F of Y and F of I, if C is in F of X, F of Y, there exists some theta in I with F of theta equals C, sort of thing. Okay, which is kind of a clunky statement of this thing. But again, it's exactly what you want to be true, right? If you think about the intermediate value theorem, what am I saying? Well, we've said that the continuous image of a connected set is connected. and the connected sets are precisely the intervals, right? So we're saying that the continuous image of an interval is an interval. And so if you know that the continuous image of an interval is an interval, if you give me any 2 points in the image and some point between them, there has to be something that maps to it, right? So maybe think about that one a little bit, but this is the, right, this is the intermediate value theorem. And are there any other like really nice theorems to prove from this? There isn't too much to do, precisely because number one tells us that the connected sets in R are just the intervals. Connectedness is a little bit boring in R. It gets a lot more interesting in Rn. So the mean value theorem, interestingly, is totally its own thing. Like the mean value theorem is not a consequence of the intermediate or extreme value theorems. And one thing you might notice is that in our conversation about topology, at no point did derivatives ever come up. And that's because derivatives are a completely different thing. So topology stops at continuous, right? Topology is interested in continuous things, but not differentiable whatsoever. So the mean value theorem is a statement about differentiability, right? And because it's a statement about differentiability, it really exists on an entirely differential, like different plane. Differential topology, yeah, exactly. So if you start adding a differential structure to topology, you do get something called differential topology. It's fairly hard though, right? It's actually really quite tough. It's one of the last things that we do in 257. So because you need to be very comfortable both with differentiation and with topology before you can start to merge them. But as a general rule, topology on its own is only concerned with continuity. And that's typically where the buck stops, right? So any theorems that we have related to derivatives aren't going to have a natural topological extension, right? But I can see how you're thinking, because you're thinking like, oh, all of our value theorems had analogies in topology, right? And the mean value theorem is a value theorem, so maybe it does as well. But unfortunately, no, it turns out it doesn't generalize nicely, okay? Well, actually, really, so this is basically the last class of this semester. So everyone, just as a reminder, and I'll post an announcement about this as well, Tuesday's lecture is going to just be office hours, right? So I'm going, like classes are canceled. You all have final exams that you have to worry about. So I'm not going to introduce any new material whatsoever. I will be here Tuesday, right? So in this lecture and everything like that, I will be here. So if anyone wants to come and hang out or ask questions, I'll be around, but I'm not going to cover any content whatsoever. So the last class is today. Yeah, I wouldn't be too upset if you asked 102 stuff. Like I said, I'm going to be here anyway. But yeah, so this is the last class, and you can come on Tuesday if you want, but you know, it's not going to be 157 typical stuff. Does the test contain what we covered today? No, the test would have stopped on Thursday, last Thursday. So technically the test could cover some topology stuff, namely the topology, exactly the stuff that we did on Thursday about open balls and that sort of stuff. But yeah, nothing that we did this week. That being said, if a topology question shows up on the test and you want to use stuff that we did this week, you're absolutely free to. For example, if you want to show that a set is open, it really can often be helpful to show that it is the preimage of something else under a continuous map. That can be a very useful thing, which you could use. But yeah, none of this stuff will be on the test. Okay, everyone? Are there any other questions? If only 102 allowed it to. Yeah, I don't know what to say. Especially because, you know, if you've taken 157, you know, or even, this is funny because it applies to the 137 students too. In 137, they do in the first 3 weeks what is effectively the first 6 or 7 weeks of 102. So, you know, those 137 students would jump into 102 and be like, oh, well, I know what induction is, or I know what contrapositive is, but wouldn't be allowed to use it for whatever reason. Whereas in 157, I don't really cover those things because I kind of assume that you know them. But yeah, I don't think there's too many places though in 102 where being able to use stuff from later in the course would really help you. But there might be a couple places. Okay. Yeah, it's funny if like you're doing better in 157 than in 102, but I mean, it's certainly possible, right? Like it's not unheard of. There are definitely cases where this has happened. Well, it is what it is. Yeah, I don't know. And you know what? Again, some people are good with analysis and maybe weaker on algebra and vice versa. Like that stuff happens, right? Like that's not an indictment of you or your skill or anything like that. That's just, how stuff goes. But yeah, so well, you need to be okay at simulating 3D space because it turns out most of real life happens in 3 dimensions, right? So it's hard though. It is hard to get a grasp on that, and that's definitely one of the main obstacles that we find when we teach second year, whether it's 232, 237, or 257, is having students be able to visualize 3-dimensional spaces and rotations and reflections and things like this in 3 dimensions. That's a hard thing. One day though, oh yes, thank you. Yeah, that's our ivy, which is like crazy long, and then that's our spider plant. But yeah, you do need to do it eventually, so it is kind of worth doing. I can have my phone leave now. Okay, but everyone, I'm going to go because I have to fix my computer before the rest of my lectures, and so who knows how long that's going to take, right? Otherwise, don't forget you have a test. Yeah, don't forget you have a test tonight. I'm certain that none of you have forgotten that. And yeah, right. For those of you who come to lecture on Tuesday, cool. I'll see you then. For the rest of you, I probably won't see you again until January. So, have a good break. Hopefully your final exams go well. And I will see you on the other side of December. All right. Thanks, everyone. Absolutely. You too. Thank you. See you later.